Let's now talk about a great theorem for simplifying the analysis of circuits called Thévenin's theorem. Now, it is an actual theorem that has to do with linear systems, but we're just going to use the results of it. And so imagine that you have some complicated system of voltage supplies, resistors, and current supplies, all of which are linear in their IV relationships. And imagine that they're in some circuit, and out of that circuit we pick two nodes, and we want to measure the result of everything that goes inside this circuit, which we haven't specified here, just as the result of what happens between the two nodes. Now, to be a little more specific, I have an actual circuit here, and I've picked two nodes, which are these two interior nodes. It can be any two nodes of the circuit. And the idea is, by looking at those two nodes, and I've pulled them out with these leads, but since they're just wires connecting them, these open circles are equivalent to the nodes there. And the idea is we can replace all of this with a black box, a circuit element black box, and just look at the result coming out from the nodes. And so the first thing we might ask is, what is the voltage between the two nodes, measured with a voltmeter? And that's essentially what is the voltage when those two nodes are connected by an open circuit in this abstraction. So we can call that voltage open. Open circuit here doesn't mean that it's open here. Obviously, in this particular example there are various connections between the nodes, but we haven't added anything ourselves between the two. And so we can imagine this on a graph, an IV characteristic graph, where here's I and here's V, and we've measured the voltage here, V open. And because it's an open circuit, clearly there's no current flowing, and so that's why we put this on the I equals 0 axis. Then we can imagine connecting our own resistor in between here and measuring the current that flows. And I'm going to draw that current in a funny way, because the current I actually want is the current with respect to this circuit element, the black box that represents the complicated circuit. And it has to flow into, the current as defined has to flow into the positive side to get the right definition. So I'm going to define I to flow this way. But of course, if the voltage here is plus here and minus there, the current is actually going to flow this way. So the current I'm going to get is a negative number. That's because it describes the black box and not the resistor. And so I can imagine that I put some resistor in whatever it is, and I get a So then, to use Thévenin's theorem, let's make that black. Thévenin's theorem basically says that we can replace any black box, any circuit element, with a voltage supply, and a resistor, and we just have to come up with a scheme for finding those two values. That scheme involves the first step, VTH, the Thevenin equivalent, is the open circuit voltage. 2, measure the current with the short circuit. And then 3, the Thevenin resistance is just the open voltage over, which is the Thevenin voltage, over the short circuit current. Now there's actually another theorem called Norton's theorem, which is similar. Any black box that contains linear elements can be replaced now not with a voltage source and a resistor, but with a current source and a resistor. But the new thing is that the resistor and the current source are in parallel and not in series. And so to find the result here, we make the first step is a short circuit to find the current IN, because if we put a short circuit between the two nodes, we just get IN directly. And then the second step is the open voltage. And in the open voltage, all the voltage comes from the current running across Rn, and so therefore we can find Rn. Is the open voltage over the short circuit current. Now, these two theorems, which are have the same content essentially, make me think of a couple things to say about voltage sources and current sources. Voltage sources like to be in series with things, and if we put two voltage sources in parallel with no resistors, we're going to end up with trouble. We'll end up with a system that's not solvable. So one should always be careful not to put ideal voltage sources in parallel. You get things that you can't solve. Likewise, one should be careful not to put, well, current sources like to be in parallel with things, and if we put two current sources in series, we're clearly going to have a problem, because they say that the current is going to be different, but they have the same current. So we can only put current sources in parallel, in series, if they have the same current.